We use numbers every single day, right? We count with them, we measure things, we literally build our entire world on them. And they feel so solid, so predictable. But what if I told you that underneath those simple numbers, there's a hidden architecture, a whole set of invisible rules that make everything, from your phone to the bridges you cross, even possible? Think about the number line you learned in school. You picture it as a solid, continuous, unbroken line. But what if it wasn't? What if it was actually filled with tiny, microscopic holes? Gaps so small you could never see them, but big enough to bring the whole house of cards of mathematics tumbling down. Well, today, we're going to find those holes, and then we're going to patch them up for good.
You see, in school, we mostly learn the how of math. How to add, how to multiply, how to solve for x. But there's a whole other level to it called mathematical analysis. And this isn't about how to do the math. It's about proving why the math works at all. It's about building our entire universe of numbers from the absolute ground up.
Let me put it another way. It's one thing to follow a recipe to bake a cake. It's a completely different thing to understand the chemistry of why flour, eggs, and sugar react to become a cake. Analysis is that chemistry for math. It's about proving that the things we just assume are true actually are. And to do that, you need an absolutely unshakable foundation. So, let's get our hard hats on and build that foundation. We're going to construct the real number system just like a skyscraper. And any big construction project needs three things: materials, blueprints, and then the final structure. For us, our bricks are going to be sets, which are really just simple collections of things. The final structure, of course, is the number system itself. But the most critical part, the part that tells us how everything fits together, those are the blueprints. And in math, we call our blueprints axioms. So, what exactly is an axiom? Well, think of it like a ground rule in a game. It's a statement so basic, so fundamental, that we all just agree it's true without needing a proof. We have to start somewhere, right? Axioms are our starting line. Without them, we can't build a single thing. Now, here's the really cool part. These axioms, they might have a fancy name, like the order-to-field axioms, but you already know them. You've been using these rules your whole life without even thinking about it. Things like, the order you add numbers in doesn't matter, or that every number has an opposite. These aren't just little math tricks, they are the fundamental blueprints for how we all agree numbers should behave. Okay, so we've got our bricks, we've got our blueprints, we've built our structure, and it looks pretty sturdy. But there's a problem. There's this tiny, almost invisible crack in our foundation that threatens to bring the whole thing crashing down. See, the number system we've built so far, with just these rules, has a name: the rational numbers. That's just a fancy way of saying all the numbers you can possibly write as a fraction. Seems pretty complete, doesn't it? You can always find another fraction between any two fractions. But here's the shocker. This number line has gaps. It's not actually solid. And the smoking gun, the piece of evidence that blows his whole thing wide open, isn't some weird, exotic number. It's one we all know. It's the square root of 2. The length of the diagonal on a simple 1x1 square. And here's the crucial fact, proven right here in our source text. The square root of 2 is irrational. But what does that word really mean? It means you literally cannot, ever, write it as a simple fraction. It's just not possible. No matter what two whole numbers you pick for the top and bottom, their ratio will never, ever equal exactly the square root of 2. So if it can't be written as a fraction, then it just plain doesn't exist in our set of rational numbers. It's a hole. It's a missing point on the number line that our blueprints just didn't account for. And this is a huge problem. I mean, if you want to do something like calculus, which is all about smooth, continuous change, these gaps make it totally impossible. Our foundation is seriously flawed. So how do we fix this mess? How do we patch up all these holes? Well, it turns out we just need one more blueprint. A single, incredibly powerful rule that seals up all the cracks and finally makes our number system, well, complete. Now, to get this new rule, we need to understand a quick idea called an upper bound. It sounds technical, but it's super simple. For any collection of numbers, an upper bound is just any number that's bigger than all of them. So, for all the numbers between 0 and 3, 5 is an upper bound. 1,000,000 is an upper bound. Easy enough, right? Okay, but out of all those possible upper bounds, what's the smallest one you can find? For our set of numbers between 0 and 3, the absolute smallest upper bound is 3 itself. This special number, the tightest possible ceiling for a set, has a name: the supremum. And here it is, the final rule,
The one we've been waiting for, the completeness axiom, and all it says is this. If you can find any upper bound for a set of numbers, then a least upper bound, a supremum, is guaranteed to exist. That's it. That's the whole rule. It might sound abstract, but its effect is absolutely world-changing.
This axiom is like mathematical mortar. It swoops in and perfectly fills every single one of those irrational holes. It guarantees that numbers like the square root of 2 finally have a place to call home on the number line. And just like that, it transforms our number system from a leaky, porous thing into the solid, continuous line we always thought it was. We finally have what we called the real numbers.
So we did it. We've repaired our foundation. It's solid, it's complete, it's totally rigorous. The big question now is, what can we build on top of it? What's the real payoff for all of this hard work?
Well, the answer is basically everything in modern math. Specifically, we can now build the entire magnificent structure of calculus. The most fundamental idea in all of calculus is the concept of a limit. This idea of what happens as things get infinitely close to something else. And now, with our complete number line, we can finally define it with perfect precision.
Now, the formal definition of a limit can look a little intimidating, but just think of it like a game. You challenge me by picking a ridiculously tiny distance, let's call it epsilon. And I win the game if I can always find a point in my sequence where every single number after that point is even closer to the limit than the tiny distance you picked. If I can win no matter how small you make your epsilon, we've got a limit.
And how do we actually measure that distance precisely? Well, that's where this guy comes in, the absolute value function. That simple V-shape is the perfect tool for the job. It gives us the pure positive distance between any 2 points on our number line, no questions asked. It's what makes the definition of a limit totally airtight.
So why does any of this matter outside of a math class? Because this rigorous foundation is what modern science and engineering are literally built on. It's what ensures the calculus used to design a skyscraper or send a rocket to Mars is actually sound. It's not just based on a guess that the number line is solid, it's based on a proof. It transforms math from just a useful tool for getting answers into a language that can give us absolute certainty.
It really makes you stop and think, doesn't it? We started with something as simple as the number line, and we discovered this whole hidden, complex world underneath it that holds everything together. It kind of begs the question, what other simple, obvious truths in our lives are also built on a foundation of deep, powerful, and totally hidden rules?